between these methods. And sorry. The first one works as both end-access sensors, and the second one, POTDR, is a single end-access sensors. So you can see the division within these groups. Single end-access sensors, they are OTDRs, OFDRs, and OCDR. OCDR is a optical correlation domain reflectometry, and its division during optical correlation domain reflectometry. I know that you all know how it works. And about the others, Rayleigh OTDR, Raman OTDR, Brilliant OTDR, Rayleigh OFDR. We can talk about this part of fiber optic sensors and reflectometers kinds, and in the frequency domain, we can also arrange the setup of Brilliant optical frequency domain reflectometer. It is rather interesting, and I hope we will discuss this setup in our future meetings, because I didn't prepare the presentation for this yet. So why should we use the optical frequency domain reflectometer? First of all, you know that there are a lot of dead zones within the OTDR trace, and they depend on the OTDR pulse length and some other characteristics. For example, if you have the APC connection right here, or somewhere here within the OTDR trace, we can see that its length is about 8 meters. What does it mean? Does it mean that your APC connection is about 8 meters? No, of course. This is because you have the OTDR pulse and you cannot reach the high resolution. Another disadvantage is that you have very short pulse, and after that you need to provide the continuous silence within the OTDR trace, because the pulse needs to travel toward the end of the fiber. It needs to go back to the photodiode, and only after that you need to emit another short pulse. Of course, in general, in the line, you will not have very high power to reach high SNR and to measure fibers with high attenuation, for example, like erbium doped fibers or holmium doped fibers, and so on. So to increase, to get higher resolution, the OFDR principle is a perfect solution. And here we have two different, to be honest, it is a simple, the same setup, but with some variations. You can see the Michelson interferometer. You can see digital to analog converter, signal generator, and tunable narrowband source. It means that the frequency of this laser is linearly sweeping within the range, within some range. Is usually this range at about tens of nanometers, and after that it goes to the beam splitter and divides by two paths. The first path is ended by the mirror, and the second path is connected to the fiber under test. So what do we have here? What do we have here? The sweeping light goes here. It is scattered and reflected within the fiber at each point of the fiber, and of course in the end of the fiber when we have the backscattering reflection. And at each point it is going back, and goes to the beam splitter again. And the same thing happens here. The light is reflected by mirror and going to the beam splitter. So when they meet here, the frequency of light in this arm and in this arm are different. So they are different, but they are near standing frequencies. And what happened then? We have the interference of these signals, and the interference beating will be related with the coordinate of some scattering element in the fiber at each point. And the intensity of this will be related with the Rayleigh scattering in this point, or Fresnel reflection in the end of the line. So we can see that there are some differences in this setup. We can see that here we have the polarization beam splitter. We have found out, and it's written in a lot of publications, that the polarization of the backscattered signal is not always constant, and we have to record the both states of the polarization, and after that we have to reconstruct the overall signal from these signals. Here's a basic theory. You can see the electric field of the reference arm. Here it is, and you can see the field of light going back from the sensing arm. And after some simplifications, we can write down the intensity of the photodetector. We can transform the E function using the well-known formula to cosine and imaginary part multiplied by sine function. We can see that the photodetector registers only real part of this signal, and this is why we have this at the cosine function. And we can see that FB gamma tau is a beating frequency, which is proportional to the length of the fiber on the test, just like I said before. Here's the very simple principle how the OFDR setup works, and I hope that it is rather clear. We can see what happens at the typical OFDR trace, and what happens with the resolution. We can see the PC connection we talked about earlier, and how we can see on the OFDR trace. It has 40 microns length. It's amazing, but how it works? In reality, the laser frequency sweep is not strictly linear. So I will go forward a bit, and I can show you that if we use just a simple tunable laser source without any corrections, we can see that this PC connection is about 1.5 meters. Of course, it's lower than 8 meters that we saw at the OTDR trace, but it's not truth, yes? So we need to do something to, we need to do something to fix it. Yes. Here's the time, and here is the optical frequency of the TLS, and you can see that it's not linear. What we can do? I will go to the next slide. After that, I will go back to this slide. Sorry. What we can do? We can do the additional interferometer. It is the setup by Luna Technologies, I think, or some groups related with Luna Technologies. They call it usually trigger interferometer or auxiliary interferometer. And how it works, we have the same two lasers. It has the same non-linearities within the signal, and the light goes to a coupler, and 90% of this light goes to the measurement interferometer, and just 10% or even more in some setups, even less, sorry, in some setups goes to the trigger interferometer. Here we have the different arms of interferometer. The first one has the shorter length, and the second one had the bigger length. And it means that after the traveling these arms, light will have the interference beating at a signal frequency, but only in the case if the tunable laser source sweeps strictly linear, right? But in reality, it's not linear. So if we took provide fast Fourier transform using for this signal, we can see the peak, which is slowly drifts to the left and to the right, following the non-linearities of the scanning. And how could we use this information? So if we have the strictly linear sweeping, we have the harmonical function with the constant period, but in reality, we don't have it. And what we can do, we can take the points where this function raises the axis, the x-axis, and we can use these points to be for the extraction from the measurement channel. Only these points, and I don't know how to describe this. Maybe some of you play in the bands, in orchestras, and you know that if the drummer has metronome in his headphones, he could provide tempo for all other musicians. But if the song has some tempo drifts provided by the composer, you need to hurry up or slow down, and this is how this auxiliary interferometer works. So it provides some click, some clock signal, and we extract the points only from this clock. So after that, we can see that -3 decibels PC connection, instead of 1.5 meters, we have that its length is about 40 microns. Amazing, really amazing. But this method has some disadvantages because we have a lot of points in the raw signal, and after that we take only these points, and maybe it is 10 times the amount of points will be less in 10 times or 5 times. It means that the resolution could decrease, or signal to noise ratio could decrease, but we will not have here the effect of the non-linearities in the signal. So another way is to do this, is to provide some cross lines, not only in the zero, but in some different areas at equal distance, and to take more points. And these procedures are also working and widespread for the OFDR. So I will go back to a couple of slides. I will show the OFDR trace after the zero crossing, and we can see that it's a bit noised. If you can see that the reference says that it's about the modulator integrated optical element, which has about 5 centimeters length. And we need to see not only the reflections within these elements, but we need also to see the relief within this element. And to do this, we need to provide denoising. In this publication, we provided the filtering using the dynamic averaging, using the method which is similar with currency course filtering. So if we have some signal, if we have a very high signal, the averaging window becomes very small. And if we have the signal somewhere in the field of noise, we can average with the bigger window. And I think this is the most simple and the simplest and one of the most effective methods. But I know that some researchers do other things. For example, we can see that for Luna technologies, we have some advanced analysis software. We don't know how it works. Nobody knows how it works. But they do it some other way. So again, about Luna, sorry for this, but these guys are very experienced in OFDRs. This is conventional instrument data example, and we have that we have screenshot from the Luna software, and at this screenshot we have some elements within the fiber optic installations. It's written there that they are fiber Bragg ratings, and using this marker we can see the reflection at every point. We can perform the high precision length measurement of every element and distance between them. And if we put two markers, for example, here and here, we can estimate the attenuation within the line and to see how the signal changes after, before and after this installation. Additionally, we can use another window and put the marker and see that we can see the spectrum at each point. It's very useful because we have the tunable laser source, and it means that we can provide the spectrum scanning. And moving this marker, we can see the spectrum at every point. I think this is very good. So let's go back to, sorry, not back. Let's go to applications of some different OFDR systems. Let's start with metrology applications, and sorry, it's written that it's metrology, and here we see that sensing. Sorry, my mistake. Metrology applications. I will use for the references some review papers prepared by some different research group. The first review paper is Professor Zhen Yanding and his co-authors. The second one is prepared by Hideaki Murayama from Japan, and it has information about distributed sampling with OFDR and its application to the structural health monitoring. Of course, all these publications you can access using the hyperlinks in the slides. And the third is prepared by our team. Oh, it's me. Here's me. He's Dr. Fedor Barkov and our colleague, Dr. Roman Ponomarev, who is working in the field of integrated optic element studies. And this review is focused on the metrological applications of optical reflectometry, different kinds of reflectometry, not only the OFDR. And you can access this at ResearchGate or at the journal site. So what what is the general advantage of the OFDR? That we can emit constantly in the line. We don't need the pulses between the pulses. It means that we can provide the measurement with higher signal to noise ratios, and this is very old publication, but all these methods still work. July 1998, this group of researchers showed that the OFDR works with rather big lengths of active erbium doped fibers. Imagine that these fibers usually have attenuation at 1.5 microns, about 30 decibels per meter, not per kilometer, but even per meter. So it has very high attenuation in the sweeping range of the OFDR. But just like I said before, if we could sweep linearly on the time without some breaks, and we can acquire the signal all the time. Moreover, we can amplify a signal after before the registration of the photodiode. So we can see that these fibers will have rather high attenuation on the plot. And what happens when increasing the pump power, the OFDR trace goes up, and we can see that we can tune the pump power to measure all kinds of different active optical fibers. So the general application in metrology for the OFDR is the measurement of assemblies and setups and some different installations with optical fibers, optical circuits, optical elements, and so on. And you can see that all these things could be seen at the OFDR trace, just like we saw it before. We can see the connector, we can see the grating, we can see the fiber termination, and if we increase this part of the picture, we can see the attenuation, we can see the noises, field of the noise, and we can see the early scattering here, and differences between the early scattering and the noises. So a lot of different artifacts we can see at this OFDR traces, and it is a general application for metrology OFDRs at present. So another OFDR system, which is testing the FBGs, different FBGs prepared by different procedures. We can see that here we have not like microsound interferometer, but it's like a Mach-Zehnder interferometer. And also we have the polarization controller, which helps us to control polarization, and polarization beam splitter. It provides the quality of the signal within the grating. It is very important if the authors of this publication need to classify some gratings within the OFDR trace, and this is very important for this. Then we consider the integrated optical studies. This is the publication of our laboratory too. Not like previous one, but like the publications a couple of slides before. So this is related with the integrated modulator tests in the thermal chamber. Here we performed the study of paraelectric effect on proton exchange channel wavegates in lithium niobate. You can see at this graph, that the length of this modulator is about maybe this is some misprint. It should be about 5 centimeters. Sorry, no, sure, it's a typo. The length of this modulator is about 5 centimeters, and we have tested this in the thermal chamber using the OFDR, and we used the setup organized as a Michelson interferometer. And using this method, we have seen that these peaks corresponding to the start of the modulator and the end of the modulator, or channel splitting within the modulator. Here it is. They are drifting because of the temperature, because of the material of the modulator, lithium niobate, and we did some trials for measuring the signal phase and to understand how the signal phase is related with the piezoelectric effect in this modulator. And of course, you can see, you can read this in this publication too. Another popular application of the OFDR setup is the refractive index characterization. They use the relationship between the correlation function of the backward Fourier transforms of the signal and distance, and they use this relation to get the refractive index at every point. This is very important for the ones who produces integrated optic schemes, integrated optic modulators, and for the ones who produce special optical fibers and who need to control the refractive index along the fiber. If the fiber is not linear, they need to control it not only in the preform, but for example, in the already produced fiber. Another topic of my talk is PM fibers characterization. This is very important for the manufacturers of PM fibers and for the ones who use the PM fibers in distributed fiber optic sensors. For example, in dynamic break gratings. It's not secret that for most of all these applications, we need to keep the constant and high birefringence along the fiber. And how to measure this? Of course, we could use some methods like white light interferometry, but it's rather expensive. And the signal obtained by this instrument is rather noisy, even more than we have here at this OFDR trace. So the best way is to use some back reflection method, I think. And what the authors of this publication do? They use the conventional metrology setup of the OFDR. They have the polarization controller in the one of the arms of measurement interferometer, and they have the polarization beam splitter and two photodetectors registering two states of polarization, S and P. Then they do zero crossing or some procedure to make the resolution better. If we have some fiber like panda, for example, its beating, polarizational beating is about a couple of millimeters. So we cannot use the OTDR technique to see these beatings. If we have a semi-fibers using for conventional telecommunication lines, we could use OTDR and to measure birefringence, to measure dispersion in these fibers. But here we have only 2 millimeters beating. So we need to do the zero crossing for this signal. And if we zoom, if we enlarge this part of the FDR trace, we can see that all these beatings are here. And after that, we could do provide the Fourier transform in the window, in the sliding window for this OFDR trace, and could see the period of this beating, the frequency of this beating, which is easily converted to the birefringence. So we can see that using this information, we could obtain the relationship, the function of the birefringence along the fiber. This is very important for the fiber production. Another direction is optical elements docking monitoring. You know that in the integrated optical elements like modulators need to be connected with the fibers to let the signal in and to let the signal out. And how it works? Usually we need to dock the fibers using the both ends, but it's not very useful, and it's rather complicated in some cases. What we thought about that we could use for this the OFDR. It's our publication too. You can access this at ResearchGate and request the full text if needed. This setup allows us to connect using only single end access. Of course, we can see the both ends here, but in reality, sometimes the user has only this part of the setup. So we need only this reflection. And if we need the reflection from this side, we could extract this too. So we could control both reflections, or we can use the connection using only one side access connection with this OFDR. And as a final part of metrology applications in this presentation, I could show you the so-called integrated OFDR on chip. You know that there are some very popular directions in the technology, like laboratory on chip and so on. And these guys provided the reflectometer made on chip. Amazing, huh? Here is the OFDR trace acquired by this reflectometer, and here is the OFDR trace acquired by conventional reflectometer, and they're almost the same. And I don't know how to imagine this, but these reflectometers can test them both. So when an OFDR can test another OFDR, I think this is amazing. So let's go to the sensing OFDR. As you can see from this picture, the setup of the sensing OFDR is almost the same. We can see the measurement interferometer. We can see the couplers, the circulator, and the fiber on the test with some impacts on the fiber. And we can see the auxiliary or additional or clock interferometer, which is used to compensate the linearity of the laser frequency. And after that, both of these signals go to digital acquisition part of this setup. And after that, we can do some mathematical operations. So this slide is only about the mathematical operations. To perform the measurement, actually, we need to provide two measurements. The first one is so-called reference signal. We need to provide this when the fiber on the test has no any impacts on this. So we don't apply the temperature, we don't apply strain, we don't apply acoustic vibrations, we just set up this sensor into the object and do the reference measurement. And after that, this measurement should be compared with the measurement signal and to extract some impacts on the fiber. So what happens? After acquiring the signal, we can provide discrete Fourier transform for both signals and to extract the phase spectrum. Before this, we saw the OFDR trace, and I need to mention that these traces were just a real part of this signal. So we need to extract the phase spectrum, to extract the phase drifts within the signal and their connections, and to connect them with the temperatures and strains. After that, the authors of this publication provide their own procedure. You can read about this procedure more using this link in their publications. They do so-called segmentation of phase or phase correction. After that, they take integral phase and provide the phase on ROP. And after that, they convert it to fiber length change. So it is related to the deformations. Very simple principle, because we don't need to provide any additional Fourier transforms. We just need to free spectrum in the spatial domain. And after that, they provide their own procedures. These procedures may differ from one setup to another, but the main idea is that we don't need any additional transforms of this signal. We just need to extract the phase spectrum in the spatial domain. Here are the results. We can see that this is strains, and they vary from 50 microstrains to 300 microstrains, and they acquired the resolution about 12 millimeters, and the resolution in strains is about 10 microstrains. So another way to extract the signal is a bit more complicated in comparison with the previous one. The same as before, we need to provide the reference measurement and the measurement. And after that, we take the sliding window and travel from the start of the OFDR trace to its end. In this window, we extract this region from the both arrays of the data, and to provide the inverse Fourier transform for this data. We need this to associate the phase changes in the signal with the coordinate in the fiber. So if we take these procedures for all these procedures for the raw data, we will not see any connection with the coordinate within the fiber. But when we use the scanning window, we have its relation. So we provided the inverse Fourier transform in these windows, and after that we provide the cross correlation between two of these obtained data arrays, and we can see that these spectra are not strictly fit each other. The spectrum which is related with the measurement data is a bit shifted, and we can provide the cross correlation of these arrays and see the value of its shift. And this value will be related with the strength and temperature in the fiber. So we can see that we can extract the value which is related with the strain and temperature, just like in brilliant scattering. And we know that it's a big problem. It's a big issue. If you have this value, we need to divide to discriminate the temperature and the strain. For brilliant scattering, you know that there are some approaches like neural networks, polarization fibers, dynamic break ratings, and so on. Of course, the similar methods we have for OFDR setups. At this setup, we can see that they use two different measurement arms. And they have the same tunable laser source, and they have only one auxiliary interferometer. Other components they use for both arms, and they use these two channels to extract the data. The advantage of this setup is that the tunable laser source, which is usually very, very expensive, they don't use two tunable laser sources. They use only one laser, and here is, I think, the only advantage of this approach. Another interesting approach is to use PM fibers. So we can see that these guys used bow tie fibers, but in reality, we can use any type of polarization maintaining fiber, like Panda, for example, which has as much high resolution, as high, the highest resolution as possible. And we can see that we need to acquire again two channels, polarization of polarization P and S. And what we can see at the cross correlation plot, we can see that at this function, we could obtain two peaks, and they correspond to polarizations of the light, and this length is proportional to the birefringence. So when the temperature and strains change, both they travel with different velocities, and this is how we can build the matrix and to write down two equations and to find the source for temperature and strains using these equations. Well, let's discuss some sensing applications. I need to say that a lot of them are related with mechanics, usually, or engineering or avionics, and there are a lot of some special applications, but we will discuss only the ones that are most popular. So this is bonded joint monitoring. It's performed by the OFDR. You can access these publications. I think it's open access. And you can see that they need to provide very high resolution measurement of this joint. Its length is about 90 millimeters. So if you use some instrument like OTDR, they will not acquire this result. Or if they use fiber break ratings, they can test only a single point of this joint. But in such case, they used OFDR and test it with different forces, and they can see the profile of of the strength of this bonded joint with rather high resolution, about tens of microstrains or something about this. And the resolution of these systems was about 1 millimeter or even less. Another application is aircraft wing structure monitoring. You can search this using internet. You can find out that there are a lot of publications related with this. At the left slide, you can see the composite wing box and the test equipment for this. It is on the right slide. And they used the fiber and they put it in these lines, and they marked these sections to let them know what section of fiber has been inserted at every location of the wing. And after that, they provide the measurement and on-sea simulations, and they showed that their simulation was confirmed by the OFDR, and they achieved very high resolution for this, and their research was rather successful. Another application is cement samples test. This publication is by the researching team from our center. It is the Institute of Continuous Media Mechanics, which is the division of our Federal Research Center. They used the cement sample, and they integrated some different kinds of optical fibers within this sample of the cement. And after that, they provided the load, the tension of these samples. They provided the finite simulation using ANSYS or some other simulation software. And they verified their simulation was successful. And the same as before, they acquired the data with rather high resolution. They used the reflectometer, which allows them to acquire temperatures or strains. They don't separate temperature and strains yet. With a resolution about 10 microns. So I think this is a very good result. And there are some different publications of our research group from the Institute of Continuous Media Mechanics. You can see them and access them at the journals of website of the journals and ResearchGate. Well, another amazing application of the OFDR is shape sensing. Why the OFDR again? Because if we need to measure the shape of some object, usually this object is rather small. And if it is small, we need to acquire the data with rather high resolution. How could we do this? We can use the multi-structured fiber. Sorry, not multi-structured, of course, multi-core fiber. In such implementation, they have 7-core fiber, and the tips are connected to provide the measurement like this. So we have core 1, core 2, core 3, and so on. And if some part of this fiber is bending, we can see that we measure attenuation here, 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 and to build the model and to understand how this fiber behaves in the space. For example, in this application, they used additionally fiber break ratings for multiple fibers, and they provided more precise measurement because these measurements were based not only using the Rayleigh scattering, but also using the reflections within the fiber. And you can see that they bend the fiber, and they can show this the 3D OFDR trace. I think this is amazing. Well, another application of the OFDR is acoustic sensing. I'm not sure that the operation of OFDR-based acoustic sensors could compete with the characteristics of OTDR sensing in general. But some very interesting results we have in our research paper. This team of researchers provided the OFDR. First of all, they provided a very high scanning sweep. Another interesting thing is that to compensate the linearities, the authors use their own interferometer and inner source of sound at 3 kilohertz. And in this setup, they have acquired very high precise measurement within, you can see that it's 1 and 3, 2 meters long fiber. The vibrations within the range of tens of hertz, and I can't remember, I think it's about 40 kilohertz or something like this. Amazing results. You can access this publication using this hyperlink. Well, another interesting solution for OFDR-based acoustic sensor. The researchers from Israel, they used OFDR with the IQ detection, and they used 2 channels of the hybrid detector. Why do they use this? In reality, we can use only one part of this sweep, the first part, and then we can vary high speed decreasing of the frequency, and after that we see another sweep. In reality, this decreasing is not very high speed, so it takes time. For example, like this, if you see the arrow. They used IQ detection to use both parts of the sweep of the laser, so they increased the speed of the measurement, and this is how they organize the acoustic sensor. Another application is OFDR radiation sensor. So you know that there are a lot of most all of fiber optics, optical fibers are radiation sensitive, and we can see the Rayleigh scattering to characterize the radiation. The same as about gas sensor, they used special optical fiber to monitor this. But the setup for the OFDR is the same as we seen on the previous slides. They have Michelson interferometer. Another variation of this, and in this publication, they use different kinds of OFDRs. In some cases, they use OFDR with a coherent laser, and in some cases, they use radio frequency laser. But in general, the principle of these OFDRs are the same, and only the sensing elements and sensing setups differ. So let me tell you a couple of words as a conclusions for the main part of my presentation. We found out that OFDR-based systems can test single optic elements as well as complicated circuits with high spatial resolution. Yes, we saw this. We saw that its resolutions could be about 10 of microns, and or something like this. OVR-based systems can easily compete with almost all known distributed fiber optic sensors. I could agree with this, but at present, the price of tunable laser source, very high quality tunable laser source, is too high. But at this stage, they can only compete. If we could decrease the price of the TLS and to provide it with the coherent, very high coherence and nice tunable, nice tuning precision, linearity. We can not only to compete, but we can, I think, win other fiber optic sensors. But it's science fiction at present. So other kinds of distributed optical fiber sensors could be implemented in frequency domain. I mentioned this about the BOTDA, BOTDR, and maybe if we meet again, we could discuss it in future webinars. OFDR-based sensing systems provide, based to our knowledge, spatial resolution. We also want to use it for small objects, including the shape sensing applications. Yes, it's true. I hope that in our laboratory we could start with multi-core fibers too, and to provide some experience in future. Oh, sorry. It's not working good. And let me tell just a couple of words about our conference on optical reflectometry, metrology, and sensing, which will take part, which will be organized in May, in the 2023rd. The main topics of the conference are distributed and other fiber optic sensors, the use of reflectometry for metrology and optical fibers, cables, and networks, new applications of reflectometry-based systems, and fiber optic measurement and sensing systems in biophotonics and AV biophotonics. In our center, we have the divisions which are related with these activities. So we organized these rare sections within our conference, and this would be great if you participate in all these sections, especially in biooptics and AV biophotonics. This will be very interesting. So about important dates, just a couple of words. Early bird registration, the past date, July 4th. We will talk about the deadline. This is on December 31st. But in reality, I think we could extend the deadline in the beginning of the January. How to attend? You could visit the website you can see on the screen and acquire some information about the requirements for the publications. We are working with the Journal of Instruments and Experimental Techniques. It is distributed by Springer Nature, and it's Q3 in Scopus and Q4 in Web of Science. You just need to provide about 15,000 letters text, and after that, after it passes the revision, we will send you the email that you are welcome to our conference. Also, I would like to tell you that in parallel with the conference, we are working, me and my colleague, Dr. Philip Vakov, working as a guest editors of algorithm journals at MDPI. And our special issue is called algorithms and calculations in fiber optic and photonics. So you could send your paper to the conference and to send the extended paper to the algorithms journal. So you will have two good papers instead of one. Here is the program committee chair, Professor Gorshkov from General Physics Institute, and maybe you know this guy. Hello, Saiful, if you hear me. He is in the program committee list, and I hope to see him in May. The same as you all. I hope that we could meet you in turn in ORMS 2023. Thank you. My contacts are below. You can reach me at ResearchGate, and you can email me and at some social media. And of course, I would like to answer your question if you have them. Thank you.
Thank you very much, Yuri. Interesting talk. Let me see. If you have any, if you have any question, you can unmute and then ask the question straight away, or you can type in the chat box so you can ask. I can read the question for you. Yes, I know the guy in the box just now, Saiful. He wanted to attend. I think I'm not sure he's in. Saiful is not here. He has other business to do. Any question from the? Hello, anybody? Hey, Saiful is here. Hello. Hey, Saiful. Hello, I can hear you. Hi.
Yes, we can hear you. Hello.
Hi, Yuri.
Hello, Saiful.
Can you hear me clearly?
Yes, we can.
Sorry, I have one. I'm driving. Okay. About the OSP, can it be extended to like something like LiDAR application? So instead of using a fiber, so we use air. I think I can LiDAR application.
I can repeat the question. You're asking about can OFDR be extended to LiDAR?
Yes, sure. Of course. I think it could be, but we didn't work with such kind of setups. But we have seen that some works in this direction are conducted. But I didn't put it to this presentation. But we can discuss it if you're interested. I think after the presentation.
Okay.
I don't know the details, but I know that some trials of doing this are conducted.
One question in the chat box. Have your group explored OFDR for biological molecules?
This is a very interesting question. We have thought about the connection, the microfluidics with the OFDR. We had some ideas, but we are just at the starting point of these works. I think it's a very complicated issue because these biological molecules have they have a very big attenuation, I think, and we could not put these molecules online and to measure like optical fiber. But I think if we need some tests for single molecules, which is passing through some channel, and to test them with the sweeping light, and to combine it, for example, with some spectral analysis, I think this could work. But just like I said before, we are at the start of this research, and if you are interested, we could, you can see my email, we could discuss the details, and I think we could do first steps together.
Okay. Any other question from anyone? Well, you work with commercial OFDR, right? The things that I understand, when you work with commercial products, they do not provide you the raw data, meaning the data that you get from the commercial product is a processed data. So
Yes,
what's
of
your
course.
experience with that?
We are providing the first stage, the very simple stage of the signal processing is to, I will go back to the presentation and try to show you. Well, here is the raw data after the first stage of data processing. We have only fast Fourier transform of the signal, and here we have only the real part. So in this OFDR trace, we have in the raw data we have the sum of the cosine functions, and if we provide the fast Fourier transform, we could extract the reflections in the line and the scattering at every point. So the first stage is very, very simple. We need to provide the fast Fourier transform. But if we need to increase the resolution and to see the PC connection with the length of 40 microns, we need to provide the procedure like zero crossing. I mean, taking points of auxiliary interferometer, and then we need to provide the fast Fourier transform only for these points, which is gathered at the crossing of auxiliary interferometer line. And after that, we could see the OFDR trace, which could provide us the attenuation in line. It could provide the reflections of different elements in line, and so on. But if we need to provide the sensing measurement, I will show you the best way. It was described in the patent of Luna Technologies, but Luna used the separation of temperature strains and strains. And here's the simplified diagram of data processing. They provide a fast Fourier transform. They have the sliding window. They do inverse Fourier transform in sliding window. After that, they take correlation of this function, correlation function, and the peak of this correlation will be related with the strain and temperature in the fiber. I think this is the best method to extract the strains and temperatures if we need to use it as a sensor.
Okay, good. So it's a post-processing.
Yes, of course. If you see the raw data, it's just like a random points, and that's it. We could not understand what does it see.
Okay. All right. I think that's about it for today. Thank you very much to Yuri for the very interesting topic.
Before that, can we take
yes,
group photo?
Yeah. We are going to that. We are going forward.
Okay, cool.
Can we have can you stop sharing the screen, Yuri?
I'm not sharing the screen. Yes.
Yeah, no. Can you stop sharing the screen? We are taking a group photo, visual style, and everyone, please let me adjust the view hub. Okay. If everybody can quickly open up their video feed for a while, and then can take a quick pictures, and then can call it a day. Thank you very much for attending today. Thank you, Yuri.
Thank you.
Let's wait for everybody. There, Saiful is driving.
Yes.
Okay. Somebody, maybe Min, can you
Yeah, boleh.
Snap.
All right, on 3 guys, smile. 1, 2, 3. Okay, perfect.
Okay, thank you very much, everybody. Thank you very much again, Yuri,
Thank you.
for the talk.
Thank you for your invitation.
I hope this can be, a start of collaboration. If you want to reach Yuri, you can. Oh, maybe later you can email me the slides and then I can share with.
Yeah, sure, of course.
Yes. Thanks, Yuri. And then we will have another session, I think, next week or the following week. So wait for our announcement. We have another PLS coming.
On the 15th.
Next week.
Yeah.
Okay, on the 15th we have another PLS. So I will let you know the topics and whatnot. Thank you very much again, everybody.
Thank
Stay
you.
safe.
Thank you.
Have a nice
Good luck in your
week.
search.
Have a nice weekend ahead. All right, Yuri.
Have a nice week.
Bye.
Goodbye.